Good afternoon. I'd like to talk about a project on which we have been working for a while now, and that's on company name disambiguation. Company name disambiguation essentially means to map different surface forms of a company name to its unique formal name. And it's very similar to the idea of name entity recognition and name entity disambiguation as a general term. So to stick to the most frequent terms in the literature, from now on, I will be talking about NER and NED instead. The idea is that we have hundreds of thousands, probably millions of articles. In the first step, we need to go through all of them to extract the name entities. Since this is a company name detection and disambiguation, first we need to concentrate on the name entities of the type organization. Then we need to map each of these name entities to the real formal name. So like you observe here in this slide, there are several instantiations of the specific company, and we need to map the correct formal name to the name entities that are already detected. And depending on the context, these formal names can run from several hundred to hundreds of thousands, or in some instances, even to several million formal names, which signifies that it's not a trivial task. Of course, there are some end-to-end systems that do NER and NED in a joint model. However, for technical reasons, we prefer to use a disjoint model. First doing NER and then performing NED. So mentioning that, what are the typical approaches for these two components? Well, the state of the art in name entity recognition used to be CRF classifiers. Advent of RNNs and generally deep neural networks help the researchers to use more efficient ways to extract the features and use those features to feed their CRFs, and in this way enhance their models. And then some other people start to use CNNs as a way to extract the character base or character level features. As we know, the attributes of characters sometimes have strong signals about an entity. For instance, having a capital letter in the beginning of an entity is a strong signal that that's a named entity. And finally, we had transformers people try to use to replace basically the time-consuming and computationally demanding architectures of LSTMs or GIUs with light architectures of CNNs and attentions in a transformer model. In the part of disambiguation, there are generally two categories of models called parameterless and parametric. Let's not confuse these two approaches with the parametric and non-parametric in statistics. Parameterless essentially means that we just have a function which computes the similarity between surface forms and formal forms or formal names. These functions are essentially quite fast, but the problem is that they cannot be transferred to other domains, so they have domain adaptability problem. In contrast, parametric models learn a model with parameters. They can be transferred to other domains with general approaches for transfer learning, for instance. However, they are mostly more time consuming and in respect to parameterless approaches. So to get the good out of both worlds, we decide to combine these two approaches in a hybrid way. So in the first step, we use a similarity function like cosine and compute the similarity score between each entities and all available formal names. It's been done in a very efficient way using the cosine computation on sparse matrix. And then we use those features as those scores as a feature in addition to the vectors of formal names and source names generated by extracting the TF-IDF n-gram characters of the n-gram of the characters of the names and feed all of them into a deep model. In this model, we had two channels, one channel for source name and true target name, and one channel for false target name and source name, both of them associated with their scores. The vectors of the names, which were essentially, like I mentioned, the TF-IDF vectors of n-gram characters of names, were traveled through several layers. And at the end, we used a hinge loss function to compute a score given each combination. So in this loss function, we had the similarity using a function. We computed similarity of the generated vectors for source name and true target name and source name and false target name with their scores, multiplied with their associated scores. We had two sets of data sets. One of them was a proprietary data set belonging to a company on 20 languages. Of course, the statistics mentioned here are for the English version. For other languages, we had less data. Nevertheless, we try to use this approach on multilingual using the multilingual embeddings of laser and, of course, the same mechanism for extracting the TF-IDF vectors. And then we also tried our model for other publicly available datasets to compare our work with the others. And here are the results. The first three rows are baselines, and the others are our contribution. 1n, 2n, and 5n means how many negative samples we have used per true sample. So how many negative samples per positive sample have been used for training. And ordered means that how we collect those negative samples. Are they collected from the vector of most similar negative samples to the true sample or not? They are just randomly collected. No score is an ablation study to find out the importance of pre-computed scores. So essentially, we remove this from the learning from the objective function. All the models are trained using the similarity function called geometric mean of Euclidean sigmoid dot product, proposed by Feng et al. To investigate the capability of this function in contrast to cosine, we also run a model using cosine as the similarity function. Also, all the models at evaluation time use a window of the most similar source name or formal names. In contrast to the last models that evaluated over all possible formal names. There are two highlights about the results that I like to pinpoint. First, the state-of-the-art results that out of 4 datasets, we got 3 state-of-the-art results for 3 datasets. And second, the robustness of the model, which can be realized by comparison the full target with ordered model. Ordered models evaluated only on the window of formal names, while full target evaluated on the full sets of formal names, which is not possible in a industrial strength application. because of the time it requires, but you observe that the results are not that much different from each other. So by computing the scores in a pre-processed and feeding them into the a learning function, we managed to scale a system for an industrial strength application. Thank you very much.